Hey everyone, and welcome. Sound, it's literally everywhere, right? The music we listen to, the conversations we have, it's just a constant part of our lives. But have you ever, really stopped and thought about what it is? Well, today we're going to do just that. We're going to uncover the amazing science behind this thing we take for granted. So let's dive right in. I mean, seriously, think about it. You clap your hands, and somehow that action creates this invisible thing that travels across the room and hits your ears. It feels like magic, but nope, it's pure physics. So what is this energy? Where does it even come from? And how on earth does it get from point A to point B? Okay, so here's our game plan for this explainer. We're going to start at the very beginning, the secret origin of sound. Then we'll follow its journey. We'll learn how to talk about it like a pro, get into the cool world of echoes, and even explore sounds that are totally hidden from us. And to wrap it all up, we'll see how we use this science in some really amazing ways. All right, first up, where does sound even begin? The answer is actually so simple, and it's happening constantly all around us. There is one thing, one absolute must-have ingredient for any sound to exist, and that's vibration. So yeah, that's the big secret. Sound is basically a type of energy, and this energy only gets created when an object, literally anything, starts to vibrate. That quick little back and forth movement, that's the spark that starts the whole fire. And you know what's cool? We can actually prove this so easily. Take a tuning fork, you strike it, and boom, you hear a sound. Simple enough. But then, if you touch it, you can actually feel it shaking, right? That's the vibration. Even better, touch that vibrating fork to a little hanging ball or the top of some water, and you can literally see the energy transfer. The ball will jump, the water will ripple. It's such a perfect visual proof. And look, this isn't just some weird tuning fork thing. This is the rule for every single sound. The sound of my voice right now, that's my vocal cords vibrating. That buzzing sound a bee makes, that's its tiny wings vibrating at an insane speed. No matter what the sound is, it always starts with a vibration. Okay, so we've got our vibration. But so what? How does that shaking from, let's say, a bell ringing over there actually get into my ear over here? Well, it can't just teleport. It needs something to travel through. It needs a ride. And that ride has a scientific name, a medium. This is super important. Sound can't travel in empty space, like in a vacuum. It needs stuff. It needs particles to pass its energy along. And that medium can be a gas, like the air we're all breathing, a liquid, like water, or even a solid, like a door or the ground. Now here's a really important thing to get your head around. It's kind of like a line of dominoes. You push the first one, and what happens? The wave of falling dominoes zips right down the line. But each domino itself doesn't actually go anywhere, right? It just falls over. Sound is exactly like that. The air particles just bump into the ones next to them, which bump into the next ones, and so on. It's a chain reaction. The energy travels, but the particles themselves just kind of wiggle back and forth in their own spot. So what does this chain reaction actually look like? Well, as the vibrating thing moves forward, it pushes the air particles together, cramming them into a little high-pressure area. We call that a compression. Then, when it moves back, it leaves an empty space, a low-pressure area, called a rarefaction. So a sound wave is really just this repeating pattern of squished-up particles and spread-out particles moving through the air. Okay, so we've got this pressure wave traveling along. But obviously not all sounds are the same, right? A tiny whistle sounds completely different from a deep bass drum. So how do we actually describe these differences? Well, for that, we need to speak the language of acoustics. It really just boils down to three main things. To describe any sound wave, you just need to know its frequency, its amplitude, and its speed. Let's quickly break each one down. First, we have frequency. This is basically how fast the wave is vibrating. How many of those squished and stretched out parts pass by you every second? And what we hear as frequency is pitch. A high frequency means lots of vibrations, which our brain hears as a high-pitched sound, like a flute. A low frequency is a low-pitched sound, like a bass guitar. And we measure it in something called hertz, or Hz. Next up, amplitude. If frequency is about how fast the wave vibrates, amplitude is about how big the vibration is. It's the amount of energy in the wave. And for us, amplitude is just loudness. A quiet whisper has a tiny amplitude. A loud rock concert has a massive amplitude. Simple as that. And last but not least, speed. This is where things get really cool. The speed of sound isn't one fixed number. It completely depends on what it's traveling through. You know how you always see lightning before you hear the thunder?
That's because light is insanely fast, but sound in air is, well, it's kind of slow, just about 346 meters per second. But put that same sound in water, and it suddenly speeds up to over 1,500 meters per second. And in something solid, like steel, it's flying at almost 6,000 meters per second. The medium is a total game changer.
Yeah, just look at this comparison. It makes it so obvious. You can see the speed just skyrockets as you go from gas to liquid to solid. And why? Well, it makes sense, right? In a solid, all the particles are packed super tightly together. So when one vibrates, it immediately bumps into its neighbor. In a gas, the particles are all spread out, so it takes more time for them to pass the energy along. So sound travels in a wave, but what happens when that wave hits a wall or a cliff? Well, just like a ball bouncing off a wall, the sound wave can bounce back too. And that bouncing sound is, of course, an echo. But here's a fun little fact. For our brain to actually register an echo as a second, separate sound, there has to be a tiny delay. Turns out, our brain holds onto a sound for about 1/10 of a second. So the reflected sound has to get back to us after that little moment has passed. Otherwise, it all just mushes together.
And that time delay means there's a minimum distance for an echo to happen. If you do the math, sound travels about 34 meters in that 0.1 seconds. But remember, the sound has to go there and back. So the wall or cliff needs to be at least half that distance away, which comes out to about 17.2 meters. Any closer, and you won't hear a clear echo.
But we humans are pretty smart. We don't just leave echoes to chance in big, empty valleys. We've actually learned to control and use sound reflection in all sorts of clever ways. Think about megaphones, or a doctor's stethoscope, or even the curved ceilings in a big concert hall. All of those are designed specifically to manipulate sound reflections. Yeah, look here. A megaphone or a horn is shaped like a cone for a reason. It takes the sound waves and uses a bunch of tiny, quick reflections to bounce them all forward in one focused beam, instead of letting them spread out everywhere. And a stethoscope? It's the same idea. It captures the super faint sounds of your body and uses reflections inside its tube to guide them straight to the doctor's ears. Okay, so we've been talking all about the sounds we can hear, but what if I told you that we're actually missing out on most of the sounds out there? Our hearing range is actually pretty small. There's a whole universe of sound that's either too low-pitched or too high-pitched for our ears to even notice. So for us humans, the sweet spot is between about 20 hertz and 20,000 hertz. Anything below that is called infrasound, these super deep rumbles that elephants use to talk to each other across huge distances. And then anything above 20,000 hertz is ultrasound. And that's the secret weapon for animals like bats and dolphins, who use it like a superpower for navigating and hunting. So even though we can't hear ultrasound ourselves, we have figured out how to use it. And let me tell you, these super high-frequency sound waves have become an incredibly powerful tool, especially in industry and medicine. For example, in factories, they use ultrasound for super deep cleaning. They'll shoot these waves into a cleaning liquid, and the intense vibrations literally shake the dirt and grease off of tiny, delicate parts. It can even be used to see inside solid metal to find cracks you'd never spot with your eyes. And of course, the one we all know, sonograms in hospitals. They use the exact same idea of sound waves bouncing back to create those first amazing pictures of a baby. So there you have it. From a tiny little vibration to a tool that lets us see inside our own bodies, the science of sound is just incredible. It's working all around us, shaping our world in ways we rarely even think about. And it really makes you wonder, right? What's next? What other amazing things will we be able to do with sound as we learn more about it? The possibilities are kind of endless.